I'll just do that. So there are two kinds of relativity. One is special, another one is general. Okay. So far we haven't talked about, the length of a meter stick can be different if, you observe it versus I observe it. If we are in relative motion, that means we are moving with respect to each other. So for example, if you are riding a car and I'm standing on the road, and if we were to measure the length of the same thing, being in two different frames, what happens? So far we assumed, okay, it's not going to change. But the main thing about this theory is that it does change. Okay, it does change, and there are going to be measurable difference if the relative speed is relatively large. Okay, and so that's the main thing. So yes. So I'll just let you read this one here. So what happens is constant velocity is a special case of acceleration. So when things are accelerating, we know that means the velocity is changing. So if velocity is not changing, we call it constant velocity. So the special theory of relativity talks about the situation when the relative motion between two people or two objects, it's a constantly changing. I mean, the relative velocity is constant, okay? It's the objects are not accelerating with respect to each other. So that's the special. And when you include the acceleration, what happens is that becomes more general and more interesting too. And that's where all the idea of these black holes and so on comes in, okay? But that becomes mathematically challenging, okay, for us, for in this level. So that's why we're going to be just focusing on special theory, where the mathematics, we can actually derive that relationship between difference in length or the time by using simple geometry and Pythagorean theorem. So that's what we're going to be doing here, okay? So now, what do you think about this? So let's, go ahead, read the question and respond. And you have 1 minute and 30 seconds to answer this question. Thirty more seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. Okay. Let's see what happens here. So I see mostly B here. So can somebody help me here to understand why B is the correct answer?
It's relative to the bystander. So even though the bear is moving at a speed of 4 meters a second and the biker is at 5 meters per second, as both the bear and the cyclist move together, it only appears to the observer that it's by only 1 meter, 5 meters minus 4 meters.
Yeah, so with respect to each other, they are just moving 1 meter every second, right? So in 1 second, bicyclist gonna be 1 meter more than what it is now. In second, it's gonna be 2. Yeah, perfect. Thank you. So yes, B is the correct answer in this case. So it's the relative speed. So for example, when we are driving cars side by side on, let's say, freeway, one person 50 miles per hour, another one is also, oh, if it's freeway, let's go with a 60 or 70, let's say 70, right? 70 in one lane, 70 in another lane. What happens? They're gonna be just next to each other all the time. So that means relative to each other, they are not moving at all. Speed is 0. So we get that by just subtracting 2 speeds, right? On the other hand, if they were driving in opposite direction, then what's going to happen? If one is going 70 miles per hour to the east, another one is going 70 miles to the west, in 1 hour, how far are they going to be with respect to each other? It's going to be that 70 plus 70, right? So 140 miles per hour. So with respect to each other, it seems like it appears that they are moving 170 miles per hour, not just 70. So that's how the math works out. So there is nothing fancy about it. So this we call relative velocity, probably in physics 1. Some of you saw that, used it, or learned it, okay? But anyway, even if you did not, this is the idea, okay? So here you'll see this relative velocity coming in, quite often. So hopefully that's gonna, be helpful here. So now this video talks about the same idea here. It is about 4 minutes long, relatively a little longer than what I would like to show at once, but this is interesting and gives a lot of idea about it. And there are some questions for you to think about while watching this video, okay? And so, okay, so at very, very fast speed, this way of adding speed breaks down. You cannot add like that. So for example, if you are shining a light from a plane, then there is speed of light and plane is already flying, let's say. So if the speed of light is, we know it is 300,000 kilometers per second, and plane is already moving, let's say 50 meters per second, and then should we add those numbers based on the Galilean relativity or classical theory of relativity? Yes. So the speed of light should be whatever speed it has, c, 300,000 kilometers per second, and speed of the, light. So that's what the observer in the ground should observe, right? Just like the speed of the baseball. The observer on the ground observed, right? It was the speed of the truck plus the speed of the baseball. So speed of truck, or I should say speed of truck and speed of the baseball. Now for the light, we call speed as a c. So that's a light, and that's the speed of, let's say, plane. So that's what we get based on classical theory or the Galilean theory of relativity. But what happens? The Einstein says that is not correct. Okay, the speed of a light is going to be just equal to, or yeah, the speed of light is going to be still equal to c, even when you fire a laser light from the very fast flying plane or a spaceship, let's say. It's going to be still c, not c plus v. So that's the new idea. Okay, and to describe that, the Einstein came up with several thought experiment and gave some results. At that time, it was difficult to verify those, but later, yes, there are experimental observations, and we'll talk about a couple of them here as well. So now here is a question for you. And you have a minute to answer this question. Thirty more seconds. 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, so this bike is a super bike. Should I call it super bike? Because it's moving 95 the speed of 95% the speed of the light, 0.95 times, oops, c, and the light comes out as a c, right? So now let's see, what did we get? So we got A, B, and C, but mostly B, and that is a correct answer. So speed of light remains close to, I mean, the speed of light remains same, it's constant. That's what the special theory of relativity is, okay? And so based on the Galilean theory, we have been 1.95 C, or the answer would be C, but that theory fails, and that's the correction Einstein came up with, okay? Okay, here is this another question. So what do you think? And you have a minute again. So remember in previous question, light was, moving in same direction as a bike. Here it's moving opposite, and speed of bike is still same. So you have a minute to answer this question as well. and 30 more seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. Let's see what we got. Oh, we're still getting varieties. So the correct answer is still B. So speed of light remains constant. It does not depend on relative speed between observer and the, let's say, the object. Okay, so let's keep that in mind. That's what one postulate or one, so special theory of relativity, there are two postulates and one is this one here, okay? So the special theory of relativity, when we're talking about, we are talking about inertial frames. So that means the speed is not changing. The relative speed is not changing, okay, remains constant. So 0 is also constant, and the other numbers, as long as they are not changing, that's a constant too. So what happens is there is no difference between 0 or the other values when we look in terms of motion. Okay, so for example, let's say you are sitting on restaurant. So you say, okay, you are not moving. Restaurant is not moving. Okay, it's not one that kind of fancy revolving kind of restaurant. Let's say it's not that. Okay, so it's not moving. You are at restaurant. What happens? You can drink just fine, of course. Now, when plane is flying, and you are being served just like you are on restaurant, what happens? There isn't much difference. As long as a plane is flying at its top speed and speed is not changing, there is no turbulence, that means it's moving with constant speed, okay? When these captains announce, like now you can take off your seat belts and so on. So in that kind of situation, it's moving with constant speed. When that's the case, what happens? You can do all the activities you can do here at restaurant. Same thing. So not moving or moving with constant velocity, they are kind of equivalent. Okay, so that's what Einstein is saying. Okay, so the laws of physics are same in all inertial frames. So as long as it is inertial, as long as they are inertial, that means the relative velocity is constant. So with respect to ground, plane is moving, let's say 600 miles per hour, constant all the time. That means in that case, that's the inertial frame. Okay, so you are on the ground. So ground is one inertial frame, and plane is moving at constant speed, or I should say constant velocity with respect to ground, means that is inertial frame of reference. But when it is accelerating, then that's not inertial frame, okay? So that's one. So the laws of physics, you can apply the same laws of physics everywhere. That's what it is saying, as long as it's inertial frame. So same laws of physics working here, same laws of physics working here. So that's why you don't feel any difference, okay? And in all inertial frame of reference, speed of light is same. And that's the example we had, okay? The last two clicker question, okay? This C, or the speed of light, remains C. as long as object is not accelerating. Okay, so these are two things. So keeping speed of light same now creates some complication that we need to overcome. And that may be slightly off from our intuition, okay? And so for example, yes, in our everyday life, we have seen, okay, when you throw baseball or a fire bullet from moving object, what happens? The speed is larger than when you do that from the ground, okay? Speeds add up, we know that, okay? But here it's saying that when objects are moving relatively fast, what happens? And especially if it is light, that is not true. Okay, so yes, it is true for the light. For another object, what happens? And how do we add the speed then to not get, let's say, just straightforward, this plus that, 5 plus 10 is equal to 15. Then what's the number then? Okay, if it is moving at the speed of light, then yes, it is just c, okay, speed of light. But if it is close to speed of light, then when we add them, what happens? It does not get added straightforward ways. It is slightly complicated than that. So there is formula. We'll see how to add speeds when speeds are relatively fast. Okay. So now let's think about this one here. So no fancy here. Okay. Just usual scenario. This thing is moving, right? So this thing is moving here in this direction. So that is front. Okay. So now the flash of light that originates from here goes there and there, right? So now here is this question. So please go ahead and read and respond. And you have 1 minute and 30 seconds to respond to this. 30 more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. So I'm saying A as the correct answer. Let's say, am I right or wrong, and why? Can somebody help here? Okay. I hope you guys are still there and listening and ready to help me.
that would most likely be wrong because the train car is moving with velocity v to the right. So you wouldn't see it hit both detectors at the same time as far as you being standing on the ground.
And why is that? Because it's moving, right?
Yeah, because moving with velocity v to the right.
Right. So looks like that's not going to be correct answer. So that means this front end, front end is moving this way, means the light has to travel more distance to reach there, right? And this end gonna be closer from the point where the light originated. So light has to travel shorter distance here and longer distance here. So that means looks like it's gonna hit the back detector first. Yeah, thank you for the help. That was tough. That was tough. And most of you thought just like I did. Okay. So now we can use this idea to build on this and write the difference in time, okay? So in theory of relativity, you see this term called event, just like you saw in that question. So when we say coordinates, so far we've been using, let's say, x, y, or could be z as well, right? So it is this how far it is from there, this is how far it is from there, and maybe that much from the g. So three values, right? From both x, y, and z axis. So this is a space coordinate. When you include time in the space coordinate, what happens? That becomes the frame of reference for an event. So now you are including time. So for example, you may say, okay, there was an accident on the road outside, wherever you are, okay? And if the person, the another person want to go see the accident, that person may or may not see the accident, even the accident scene. Why? Because the accident already happened and scene may be cleared already, okay? So to specify an event, you need both place and time. Okay, so the accident happened in that intersection, right? So you can give that place, street address, and then time. It happened at 11 o'clock. So it's been already more than 1.5 hours. So most likely it's been cleared, right? So yes, so space position, and when we put the time stamp on it, what happens? It makes the frame of reference, and that's the coordinate system for this relativity we are talking about in this chapter. So just like in the past, last question we had in the previous slide, let's suppose now the light source is here, okay, and the light source emits the light, and then light travels like this, but the light source is attached to this moving object, right? So it's moving object, so that means after a certain time interval, let's say delta t, what's going to happen? The object, back of the object going to arrive here, front of the object going to arrive there, and we are saying the light reaches there, right? So for the observer who is in the car here, what happens? Light started from the back here and went there. So that's the distance traveled by light for this person. But if you are standing outside, and watching it, what happens? You see, oh, light is started here. And then now light hit the front end when car's front end is there. So that means it traveled that much distance. So these two observers don't have agreement in terms of distance traveled, okay? So same event, same phenomenon, one in one frame of reference, another one, another frame of reference, they don't agree about the event, okay? About their measurement. Now, so now this idea helps us to, came up with that the time measured by this person and this person must also be different. So how do we do it? So let's take a look here, okay? So speed of light, the speed of light is same. So what does it mean? So let's write down the equation for the speed of light. So for this observer, since the speed of light is same for this observer and that observer, remember, that's the Einstein's theory that we are trying to use here, okay? And so what happens? For both observer, the speed of light must be same according to Einstein's theory. So for this observer, speed is given by distance traveled by light and divided by the time. So whatever time this observer measured, let's say that time measured was delta t. We are denoting that. Could be any number. We are just writing delta t. In this frame of reference, that is at rest, okay? So this person is at a frame of reference, which is, frame of reference, which is at rest. And this person is moving frame of reference, is in moving frame of reference. So for the moving one, we are putting this prime, okay? And for the stationary, we are writing without prime. So for this observer, what happens? Distance travel is this, and let's say this person measures times delta t prime. So based on the definition of the speed, what happens? This displacement divided by time for both of the observer. So now, here is the problem. When we say C is same, we just notice that delta x is larger than delta x prime, right? So we know this. Since this is that and must be constant, according to Einstein, right? Special theory of relativity. So now to make this thing same, for these two being different, what we need? We need different time. These times also need to be different, right? So since delta x is larger, delta t has to be larger to make this constant. So let's put it in terms of number. Probably it's going to be a bit easier. So let's say delta x measured by this observer is some number. What should I put? Let's say 12. And time measured by this observer, delta t, is 3, right? So 12 over 3 is 4. So let's say in our world, the speed of light is 4. Let's say, just for convenience, I'm just writing some random number. Now, we need to have the C same for from the measurement of this one as well. And delta x prime is smaller, right? So let's say that number is just, how do I come up with that? Let's say 6, smaller. delta x prime is smaller than delta x. Let's say that is 6, okay? And now if we want the result of this before, then delta t prime has to be what? It looks like 1.5 gonna give you that number, right? 6 divided by 1.4 gonna give you 4. 1.5 gonna give you 4. So what does it mean? Since the distances are different, time has to be different as well. So what does it mean? So time measured by observer and another observer at two different reference frame of reference, two different frame of reference for the same event is different. Event is same. What is event here? Light started from the back of the truck or car and hit the front of the car. It's the same event for both of them. But the time they observe is different. How much is the different? Are they related? Now we need to come up with the equation, okay? So C is fixed. So for that, time has to be different. What's the relationship? And that's the relationship we want to derive. And this phenomenon is called time dilation. Okay, so yes, so that's what it is saying. Delta t has to be larger than delta t prime, and that's what we saw there. Okay, so now let's derive the relationship between two times. So this is, I'm just using Pythagorean theorem here. So looking at equation, it may look kind of scary, but it's not that bad, okay? But even if you don't understand how it is derived, make sure you understand a couple of things. And what are those things? I'll talk once we have that equation, okay? So let's have a little bit patience here. So let's suppose there is this observer who is in the car and the event is taking place right there on the car. Light gets emitted from the car, okay, and moving in the car. So the event is taking place in the car and observer is also in the car, okay. Now, so what happens here? This observer is measuring the time it takes for this light to reach to the top and come back down, okay? So it is a kind of fancy, this is also called, like the time clock, okay? What is clock? Clock is the some sort of device that measures the time interval between two events, right? So what's happening? One event, light gets emitted. Another event, light comes back, okay? So this observer is trying to observe that time, okay? So now, for this observer, what happens? Straightforward, light travels distance h while going up, height of this car, and then comes back. So total distance traveled is 2 times h, okay? And since the speed of light is c, the time it takes is delta t 0. Let's denote that by delta t 0. So this time we call proper time. So main problem of solving questions related to this relativity and time is identifying which time is the proper time. So how do we define proper time? What do we use as a proper time? the time that measured in the same frame of reference, okay? So this event is taking place in this moving car, and the observer is also in the moving car. So observer is measuring this event from this in the same frame of reference. So when you do that, that's the proper time. So right now you are sitting in your home and you are measuring time. You know, how long it takes for Ramesh to finish this slide, let's say. So what's happening there? You are in home and your clock is also right there. You are right there and you are measuring that, okay? So you are measuring time from the clock that is on the same frame of reference where you are observing the phenomenon. And that means that clock is observing the proper time. But somehow, let's say, you leave your clock in a moving car and you measure the time looking at that clock. Let's say you have a really big clock. It is stamped on the car and car is moving. You are on the ground and car is moving and you are trying to time the time from the ground where the clock is in the moving car. That time is not proper time. That we call dilated time, okay? So this is the proper time. What is proper time? When you measure time from a clock that is at the same frame of reference where the event is taking place. And by the way, when we say same frame of reference, what does it mean? As long as they are moving with same speed, or I should say velocity, what happens? Even if they are two different objects, the frame of reference is going to be same. So for example, think about a car moving 75 miles per hour to the east. Another car also moving 75 miles per hour to the east. Okay, they have same velocity. So that means this car and another car, both of them have same frame of reference. And no matter whether that car, you know, the car is at your place or in my place, as long as they are moving in with the same velocity, what happens? They are same frame of reference. So they does not have to be sitting together. They can be anywhere in this universe. And as long as they are moving with same velocity, or the relative velocity with respect to each other is zero, that means that's the same frame of reference, okay? So let's keep that in mind. And any event measured by the observer on that frame of reference, or the time measured by that observer in that frame of reference, is the proper time. And remember, the observer does not have to be on the same frame of reference. As long as clock is in that frame of reference, time given by that clock is the proper time. But if you are trying to look time from a moving clock, then that's not a proper time, okay? So the clock has to be stationary with respect to you, with respect to observer. So that's the main thing here. Okay, so this is proper time, okay? Great. So height of the car gonna be same because this car is moving this way, okay? So in the perpendicular direction, there is no difference in terms of length as well. I mean, length remains same. So let's now use that as a reference. So we are solving that as a h. I mean, we are solving that h. So now let's take a look at another observer who is standing outside that car. So since the car is moving, what that observer gonna see is this light emitted from the back. So do I have car there? Yes. So this one, it starts from here. So rather than going straight, what happens? It's gonna go a bit inclined. When it reaches to the top, what happens? Since the car has already moved, it does not go there, but rather go there, right? So that's where it meets, let's say. So slightly up, from straight up. So now, similarly, when it comes back, it's gonna travel like that. Did I draw those lines there? Yeah, looks like I have, okay. So now, what is this distance? So let's suppose the time measured by this, for this event, time measured by this observer is delta t. If that's the case, then time it takes to go from here to here gonna be half of that, right? It's halfway. So that's the time. Multiply that time by the speed of light, and since this is light that's moving, what happens? That's gonna be the distance. So this length is this much, and this length is h, which is same as this, right? Now this is moving v, speed v, and it has moved through that much time, right? So it moved for that much time, means this distance is gonna be what? P times delta t over 2. So now with this length, and that length, it makes a right triangle. And that's where we use Pythagorean theorem. So I think I have labeled that one as well. So now let's use the Pythagorean theorem on that. So this being hypotenuse, what happens? This square plus that square. So h square plus this whole thing square means v square delta t square over 4 becomes equal to this whole thing square means that. And when we square this one, this becomes delta t square over 4. So that's what you see, okay? So this is square of the hypotenuse. This is square of either one side and another side. Let's say a square plus b square is h square. So that's what we are using here, right? So now, what happens? This h is same here. And since we want to relate this time and this time, what we want to do is we want to replace this h by this one here. So when I square h here, it becomes c square delta t 0 square over 4. So I can plug that in there, okay? So that's what I'm doing here. So now let's relate delta t 0 and delta t's. So delta t here, so we want to, bring them same place, means we need to factor that. And 4 is everywhere, we can cancel that. So let's simplify this, okay? So I'm canceling 4 from each of the terms there and factoring delta t square from this side. So when I do that, I get c square minus b square on the right hand side, and left hand side is left with just this. So again, we want to relate these two times, okay? So now we can rearrange that. So delta t square gonna be this divided by this thingy there, okay? So that's delta t square, but we can write delta t. So take a square root on both sides, you get this. So this, what happens here is I did a little bit of simplification here to get rid of the c square. So I can multiply and divide this by c square here. When I do, what happens? This c square cancels with that. And this c square over this c square, this becomes 1. And that's what you see here. And this is v square over c square. Okay, that's that. Hey, and that's the relationship between these two different times. So one time we call proper time, another one is called dilated time. And this fraction here, 1 over this thingy here, this keeps on showing up everywhere, whatever quantity we try to relate, okay? So that's why it is, you know, called Lorentz factor, and it has a name and its own, you know, notation. So we use gamma to denote that, okay? So that's that. So now, when v is 0, what does it mean? Remember, v is the speed of one with respect to another one. V 0 means one is not moving with respect to another one. So when there is no relative motion between two, and that means v is equal to 0 and gamma is equal to 1, right? So when v is 0, what happens? This term becomes 0, so it becomes just 1 over 1 means 1. So gamma becomes 1 means they are same. So when velocity is 0, relative speed is 0, then what happens? Both times are same. There is no difference in time. Both observer gonna observe the same time, or both clock gonna give you the same time, okay? So that's called Lorentz factor. So let's, let's plot this thingy here, gamma and b over c, just for, you know, convenience. So that way we don't have to deal with large numbers. Otherwise c is very large number, right? So what we are doing is we are plotting b over c. So when b is equal to 0, b over c is 0. And when b is equal to c, b over c is 1, and nothing can move faster than the speed of light, means the maximum value of b over c is going to be 1. So that's why this plot starts from 0 and goes up to 1 of b over c, okay? So this area b smaller and getting larger here, okay? Larger v. So that's what it means. C being a constant is just scaling the v, okay? So that's what it is doing. So how changing v over c or v changes gamma, the factor, okay? So when v over c is 0, when it is 0, gamma is exactly equal to 1. And as long as value of v over c or value of v is very, very small compared to c, gamma is very, very close to 1. As long as v is very, very small compared to c. What happens? Gamma remains, oh, looks like R. Okay, gamma is close to 1. But as b becomes, you know, like somewhat comparable to c, then the gamma starts taking up. So for example, even in this plot, we can see this line starts becoming different than 1 starting from 0.25 here, right? So as the speed of object becomes like 25% of the speed of light, according to this graph, the value of gamma starts increasing. And by the time it becomes 90%, right? So 0.9 means 90% the speed of the light. What happens? The value of gamma becomes more than double. So the time measured by one person versus another person, one observer versus another observer, is double. Now, when speed of light becomes, speed of object becomes 1, what happens? This gamma becomes really, really large, really large. Okay, that it becomes undefined actually, because when this is 1, so 1 minus 1 is 0. Okay, 1 divided by 0 is 0. not zero, but infinity, okay? So that's why you see this becomes straight. So what it means is, since nothing can move at the speed of light other than light itself, every other object gonna have speed less than, slightly less than that. So that means the value of gamma not gonna be infinity, but it's gonna be really large. And that depends simply on the speed. So that's what it is saying. So the proper time versus dilated time, difference between those time depends on the speed, relative speed between observer and the another frame of reference, let's say where the event is taking place, okay, or two frame of references. Oh, I noticed we already passed our break time, so let's take a break at this point, okay, and I think that's what I have written here. Okay, folks, welcome back. So we're talking about the time measured by observer in one frame of reference versus another frame of reference. And whenever we say two different frame of reference, that means they are moving with certain relative speed. Keep that in mind, okay? Same frame of reference means their v is 0. Relative speed between them is 0. And two different means there is some relative speed, okay? And that's b we have here. So now let's suppose, to see how the time, since the time, proper time and diluted time, they were directly related through this one here. The gamma was relating this delta t and delta t0. Did I write that correctly? I tend to forget that, okay? Oh, yeah, I wrote other way around. Delta t is gamma times delta t0. So since these two times are related through gamma, how gamma changing tells us how time is changing, right? So that's what we looked at here. So what happens? Gamma becomes really large when V approaches C. But for our everyday life, for example, even a plane which is flying 602 miles per hour, its V in terms of meter per second going to be 269 meter per second, okay? And when we use that V in there, what do we get for gamma? We get this number. See, practically this is 1. Yes, theoretically it is different, but practically this is just 1. So that's why there is no time difference measured when there is, flying plane, the time measured by the clock that is on the flying plane versus, let's say, person in the ground. You see that? Unless your clock is really, really, really can measure all the way to this decimal place here, 3, 6, 9. So it is smaller than nanometer, okay? But if you were to go a bit faster than, this, then probably it's gonna come out around nanometer difference. So still, practically, that is not much difference for our daily life, okay? So when what happens? Time becomes practically same. So that's why we don't observe this difference in time in our daily life, okay? So now here is a question related to these two times. You have 1 minute and 30 seconds to answer this question. Oh, we have only 10 seconds. And 5 seconds. 5, 4, 3, 2, 1, and it stops. Let's see how did we do. So mostly B and D. So distance doesn't have to do anything with the difference in time interval, okay? So let's say one frame of reference could be here, another frame of reference could be another galaxy, and as long as they are moving with the same speed with respect to each other, what happens? They are same frame of reference, they are not going to be difference in time. So D seems to be the correct response here. So the clock has to be at the same place, same moving frame where event is happening, okay? So the clock, the time measured by the clock in the same frame of reference where things happening, or let's say observer is also right there and observing that time, that's the proper time. So yes, understanding this is important to solve a problem because the formula itself is simple, but which one is delta T0 versus which one is delta T? That's the confusing thing, okay? So let's keep this in mind, okay? So here is one such example. This is also called twin paradox. And you can read about it, search about it and read about it if you like, but in summary, this is what this is. Let's say your twin brother flies with the speed of that, hey, very close to the speed of light for 5 years. How much older you are here on the earth? So now it says for 5 years. With that speed. So now the V is, of course, definitely that. And when we write speed in terms of C, it becomes easier to solve problem, to find gamma thingy, okay? So that's why often it's given in terms of C, and it also avoids writing large number, okay? So that's one thing there. And the brother is flying there at that speed for 5 years. So brother is measuring the time in that spaceship, so that's why that is the proper time. So now, what happens? How long your brother is gone, that's going to be the dilated time, the time you measure by just staying on the earth, okay? So what happens here? So we can find gamma using that and see how using the V that has C makes it a bit easier to do calculation here. So when we write this in terms of C, this C also becomes C squared. So C squared on the top and the bottom, they cancel, leaving us just 1 minus 0.995. And of course, let's not forget to square it because we need to square both. B has a number times C means we need to square this whole thingy. So this becomes this times C square means C square on the top here and bottom cancels. Remember, it is just dividing the B square, not 1. So we don't have to worry about that fraction on the other side. So now this number becomes easier to do calculation with, right? And 1 over that becomes, hey, And that's a magic number that gives you gamma equal to 10, 995, right? And so the difference is time is 10. So that means delta t is going to be 10 times delta t, 50 years, okay? So let's say if your brother left at 30, oops, you were also 30, right? For your twin brother, it is 30 plus 5. The brother is coming back at 35, but whoever is waiting here gonna be 80 years old, okay? So that's kind of interesting. And this is the idea taken in this interstellar movie where dad goes for interstellar journey to save the planet, comes back to find old daughter. So here is a clip, I try to, let's say, yes, put together from the trailer, I think. So now here is a question. And you have a minute to answer this question. Thirty more seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. Okay. So it's going to be measuring the proper time. So you won't notice anything different as long as it is traveling with constant velocity, and that's what we are talking about. So yes, C is the correct time. I mean, proper time in this case, C gonna be, that gonna be the proper time, and C is the correct answer. Okay. So now, so what happens is, it's not just the clock that slows down. Rather, our whole biological system also has a clock, right? Heartbeat. It depends on heartbeat. So in 1 minute, it's beating around 60 or so times, right? And so when you are moving with constant velocity, what happens? Heartbeat slows down. That means your aging process also slows down. That's what happens, okay? So now, is there any proof? So these muons are particles that basically what happens is they kind of decay over time. So the time it takes for them to decay by half number. So if let's say right now they are at 100 of them are there, this muon particles, not 100, let's say, what happens is it gets converted into another particle actually. So when it decays. So what happens is half-life is the time it takes to, let's say, reduce those numbers. Let's say if we start from 100, so how much time it takes to get that number to 50. Remember, 50 of them got converted into different particles. So anyway, so that idea, a nuclear decay, that's going to be in nuclear physics. But we know how long it takes for a muon to decay, and that is 1.5 microsecond. Okay, so now what happens is when we look at when we try to observe those particles, we can observe some of those particles all the way down here Earth, like 55 kilometers. So they are created when cosmic high energy protons hits atmospheric molecules, right? So what happens? These high speed particles. So for example, sun is spewing a lot of mass all the time. Probably you may have heard solar storm, right? So in that case, what happens? It releases a lot of mass in terms of charged particle, because sun is just a plasma charged particle, right? So they are, rushing all over in the space. So those that's rushing towards the Earth, when reaches to the atmosphere, now they collide to the atmospheric particles. And what happens? And that's when this particle is produced, muon particle, from the collision between the cosmic particle and the atmosphere, right? And so what happens? Now, their half-life is only 1.5 microsecond. So based on that, if we assume they were moving very close to the speed of light, okay, and they are particles, so that's why they cannot move at the speed of light. They have some mass, okay? So even if we were to do that, what happens? It should just decay into different particles by the time it moves through just half kilometer. What happens? When we make underground lab and try to detect those particles, we find them. So what that means? That means at their frame of reference, it's 1.5 microsecond. In our frame of reference, that must be larger, right? So what happens is, because of the time, so that's the proof of time dilation, because they are arriving, they are reaching there. Otherwise, we don't expect them to be reaching here on the Earth. Maybe one or two once in a while, not in large number. But direct proof is this. So in 1971 atomic clock, it can measure time in nanoseconds range, even more precise than that, because it is based on the oscillation of charged particle in its let's say energy level. So that's what it's measuring, and that's pretty accurate. Okay, so that's how it is built, and all our time is linked to the atomic clock. And one such atomic clock is in Boulder, National Institute of Science and Technology, right? That NIST, yeah. And so that clock, what they found was there was difference in time of 200 nanoseconds. Okay, so this plane must have, uh, flied faster than 600 meters per second. We did the calculation. Okay, so I think it was some sort of supersonic jet that can travel faster than the speed of light. So anyway, so these are the direct proof. So it's not just about equation, not just about theory. There is direct proof. And for the, for example, for the space flight and satellites that's orbiting the Earth, for them, we take account of that time difference as well, while, programming them, scheduling them, or making time measurements. We do take account of that. So now that's about time. How about length? So let's start from the time and then we can move to the length. So here is a question for you. So clock is on the wall, is at rest, right? And this rider is of course moving with the speed v, so there is relative speed between clock and the rider. An observer is also on the ground, so not moving with respect to this. So a relative speed between clock and that is v. Similarly, relative speed between observer and the rider is also v, right? So now here is question. And you have a minute to answer this question. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got. So we got C, which is correct answer. So clock is not at the same frame of reference. The observer is, right? So it's the time observed by rider is dilated time. Proper time is time observed by this observer here because clock is in this observer's frame of reference, not on this frame of reference, okay? So that's why it's a dilated time. So now we can use this idea and relate the length, okay? So time is different, right? So what happens? The length measured by these two observers at two different frame of reference also going to be different, just like we talked about, you know, the car, the distance traveled by laser light on the car, same idea, right? So let's suppose proper length measured by rider, this room length is this. And since the speed is v and time is dilated time, right? It's not delta t 0. So that's why we need to write delta t. So v is same for both of them, but time is different. So here we are writing delta t. And we know delta t and delta t 0, they are related. So we can just use that relationship here. Okay. So for this, what's going to happen? The length is going to be different because this observer is not riding on this broom. So now we can relate them. So v is same for both of them. So we can use that and solve for v from one equation and substitute that on that in another one. And use that relationship. Delta t is gamma times delta t 0. That way you can also get rid of time. So you end up picking this. So in this case, gamma, remember gamma is always, what happens? 1 or larger. Value of gamma is always 1. So when b is 0, it's 1. And when b is larger than c, sorry, b is, I should say, yeah, b is larger than 0. In that case, b over c becomes larger than 1. So gamma For moving object, gamma going to be always larger than 1. So when this is larger than 1, the L going to be shorter. So just like time becomes longer, length becomes shorter when you observe from another frame of reference. So for example, let's suppose you are standing on the road and you are watching the moving cars. Cars passing by, vehicles passing by. The length you see is a bit shorter than actual length. How much shorter? It depends on the speed. And since the speed is not that large here on our road, yeah, it doesn't make much difference, right? But let's say if you had some car, supercar that goes at the speed near the speed of the light, what would happen? Oh, that car gonna look like straight line. Remember, the length does not change perpendicular to the direction of motion. It changes only in the direction of motion, okay? So other direction is not changing. So yeah, if it is inclined, yes, it's gonna change. But once it becomes perpendicular, no change there, okay? So what happens? You will see the car, being shrunk if they were moving speed close to the speed of light. They would look funny, not the longer one, but they look like a straight line. They would look like a straight line, okay? So that's what this is telling us. So here is a question for you, and 1 minute to answer. Oh, 40 more seconds, or 20 more seconds, not 40. 10 more seconds. 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got here. B, and B seems to be correct answer. So proper length is the length measured by the observer who is on the same frame of reference, right? So length of the car means the person is measuring length of the car, means that person is on that frame of reference there. And we learned that proper length is longer than the another length, what we call contracted length, right? So yes, and that's that. So now let's look at some numbers in terms of number. So here, there is this cosmic ray particle travels directly over a football field from one goal line to another at a speed of half the speed of light. So if the length of the field between goal lines is 91.5 meter, what kind of length is that? Is that proper length or contracted length? All right, we need to decide that first. What is the length measured in the rest frame of the particle? So particle is moving. Football field is on the earth. So that means when we are talking about length of the football field, must be measured by the person on the football field there down here on the earth. So what happens in this case? is that this is going to be the proper length here, because the person who is on the football field is measuring the length of the football field, not the particle. Okay, so that's going to be proper length, and we denote that by L0, right? And speed is that. Now we can find gamma from there, and it's 15% more than 1. So it's half the speed of light. So what becomes the value of gamma? It's 15% more than 1. Okay. So by 50% the speed of light, it becomes measurably different, right? We can observe that. So that means, what is the length measured in the rest frame of the particle? So that means we want, so that means that's going to be the contracted length. And remember, so for the person who is standing on the field, particle is moving. And for the particle, what's happening? The field is moving. So when you are in a car and driving, what happens? You are not moving, but the person is standing on the road next, on the road, on the car seems to be moving backward with the same speed. You are driving the car. You, on the other hand, right there on the car seat all the time, holding the steering. You're not going anywhere from the car. You are right there on the car. So with respect to you, the person on the road is moving, and probably you may have noticed that when you look outside, things seems to be moving backward, right? And so it's with the same speed. So it's just the relative speed. And now with respect to one, another appears to be moving. So you cannot say, oh, this pill is not moving. So it's not moving when you are here, right there on the field. But if you are on the particle, let's say you are riding on plane, let's say your particle is plane, and watching at the field, what happens? Oh, it's moving opposite direction. Okay, so anyway, so that's the gamma. So now we can find the length using the formula we have for the contracted length. Okay, so it's going to be that. So that's part A. Now part B, how long does it take the particle to go from one goal line to the other according to the Earth's observer, right? And so here for the observer, there is one length. For the particle, there is different length, but they have different time as well. So we need to make sure that we are using the correct length and time. Okay, relative speed is same. So the time and length has to be chosen correctly. So in this case, time observed by, so in this case, it's asking us how long does it take for the particle to go from one goal line to the other, according to Earth's observer. So Earth's observer is making the time measurement in this case. Okay, so what we can do is we can use the length observed by the observer, which is proper length observer at the ground, right? And divide that by the speed. And remember, the speed is going to be same for both of them, so you can find that. Now, how long does it take in the rest frame of the reference? So if it is, the time measured by, let's say, particle itself, which is moving in that frame of reference, so that time is going to be the proper time for the particle, right? So we can calculate that by using this time. And if it is doing that, we can use the length observed by the particle there, which is this length, and divide that by the speed, and that's going to give you that. Okay, now these two time are just related by gamma. Okay, so that's how we use this time dilation and length contraction, folks. So how do you add speeds so that it doesn't get larger than speed of light? Remember, nothing can move faster than the speed of light. So because of that, there is this formula, and these are the relative speed due to these different ones. So for example, let's say how this formula works. Let's say one speed BPB. So that means speed of probe with respect to B is C. And this is also C. So since the speed cannot be larger than C, the C plus C has to be equal to C. And is that true? Let's do it. C plus C, 1 plus C times C over C squared. See, multiplying it means C times C. So this is C squared, this is C squared, right? So they cancel. So this becomes C plus C, 2 times C on the numerator. But in the denominator, we have 1 plus, this cancel means we have a ratio of 1, means 2C over 2 means C. So C plus C is equal to C. That's what this formula is giving. But if you use number smaller than C, then you don't get the same number. You're going to get slightly different number. So that's how the speed is done. And same thing goes with momentum and so on and so on. Okay. So what I'm going to do is I'm not going to go over that in even another class. So if you are interested, please go ahead, read through the slide and read through the book and so on. But I'm not going to be asking question from that part. I'm going to be asking question from up to this, speed thingy. So please learn how to use speed formula and the time contraction and time dilation and length contraction. Okay. So next class when we meet, we're going to go to another chapter. Okay.
Thank you.
Thank you.